So I'm going to talk to you about Go today. I apologize in advance. I only have one picture in my slide, so might not be as engaging as Phil's presentation, but hopefully you'll get something out of it. So the first thing you will all get out of this is the hot tip is that if you're ever looking up anything for Go, is Google for GoLang. Because if you search for something like Go Raft, you'll find a nice water adventure site, right? So if you want to know about, just do GoLang. So anyways, what is Go? Well, it's a programming language, obviously, but it's also a sweet mascot, which I think is always important for something because, look at how cute they are, right? So it makes it fun. But specifically, Go is an imperative language. It's compiled, and it's strongly and statically typed. So imperative, that means that it's just sort of your type out statements, and they get executed in order, right? It's not a functional language. It's compiled, so we take our Go source code, and we actually compile it down to machine code, and that's what runs. Versus something like JavaScript or Python or whatever that would be interpreted, or even Java, that will make sure I'm actually turned on here. Yeah, I'm good. Or Java that will get compiled to bytecode, which is then interpreted on a virtual machine, right? So further, an interesting point about this is that by default, everything in Go is statically linked, right? So if you have something like a C program, by default, you'll probably have a dynamically linked program where you're linked to system libraries, shared objects, or DLLs or whatever. The interesting choice that they took with Go is to make everything statically linked. So when you do a Go build and actually build your binary, you'll end up with like an 8 meg file or something, but that's everything you need to run it. You only have a small set of dependencies. You'll be linked to like, the standard C library and like maybe like a POSIX threads implementation or something. The upshot of this is that it actually makes the code, like counterintuitively, it makes the code highly portable. So you can build this program. Let's say you build it on something like Red Hat Enterprise Linux 5 or something, right? And you've linked to like glibc like 2.10. That means you can actually run it on RHEL 5, RHEL 6, RHEL 7. You can run it on Ubuntu, like 10 and up, right? So it's actually, as long as the architecture is the same, if you compiled it for 32-bit, it'll run on 32-bit and 64-bit, Intel machines. So it's almost like taking that idea of Java's write once, run anywhere, and actually working this time because you don't have to screw around with class paths, right? There are downsides to this, of course. Like it does make the binary bloated. You don't get to actually share these shared objects. So if everyone's loading in the Go runtime for their applications, it means if you have 2 Go programs running at once, they're not going to be able to share the RAM for that system
so you're saying even like
library.
Basic hello world in Go is going to be 8 meg?
No, like a hello world would be like 4 megs or whatever. But anytime you start,
that much. It's not efficiently linked. Like so.
No, it's not linked. Period. Right? It's
like again, I would. It's when I say efficiently linked. Let's say like I don't know. You're familiar with LTO, link time optimization, that GCC has done in the last since 4.6, 4.7 sort of worked. Now 4.8 actually does work. And so, that's what we just asked. So if hello world really is 4 megs, that would imply that, or I would think that it's probably not very efficiently linked, that there's a lot of stuff that's still linked in code that never would get executed.
Well, so the trivial example of hello world is not super applicable because there is a runtime under the hood that's going to be brought in anyways. So we'll continue along though, and I'll come back to the runtime later. It's also strongly and statically typed. So the strong typing is kind of like a ephemeral idea here, right? It's a term that you can apply to a certain class of languages, but static typing is something that you can strictly define, right? When a language is statically typed, any variable in that language, once you've declared that variable, it has that type for the lifetime of the variable. So in JavaScript or Python, you can take var foo and you can assign it to 1. Later on, you can assign it to bool. Later on, you can add, assign it to an object. Once you've declared it in Go, it sticks to what it is. So, as soon as anyone hears about something like that, for myself, I start to think of like probably the worst case, which would be Java, where you have to declare this variable, and you start to talk about, maybe you haven't imported the actual like the package name, so you've got these huge variable declarations and stuff, right? So my next point is that while it's statically typed, Go has type inference, so it actually doesn't end up being that bad, which is something that I really like. A few other languages have type inference. I think Scala actually goes even further than Go for it. But the gist of it here is that you can declare something up front, right? So you can say this variable gophers is of type int, and then assign the value 5 to it. Excuse me. You could just declare the variable and then later assign to it. But in for type inference here, we use the colon equals notation, and the compiler will actually infer the type of gopher holes from what you're assigning from. So here it just knows that it's 2, right? So what happens is when you're actually typing code, you don't need to worry about declaring the types up front. You can just type your names and assign them to something. If you later go and change, like let's say in a non-trivial example, instead of assigning gopher holes to 2, it's actually a function call. If you change the signature of that function to return something else, you don't need to edit all of your source again, right? It's just going to get picked up at compile time, provided your usage is still fine. So that's the first thing I like about it. Some more things that I like. It's actually quite similar in appearance to something like Python, right? So we cut back on what's sort of superfluous syntax and just get down to the content. So there's no semicolons at all unless you have 2 statements on one line, and then you use a semicolon to denote them. So here we've got our x equals 10, and there's fewer brackets all around. So in the actual case here for the if statement, you don't need to put a bracket around it. It's just, it knows that what's following if is going to be the statement there that's going to be the actual condition for the if statement. And then once a statement is done, even if it's a very large statement, you can just go right on to your curly brace and then into the body of the if. And let's see, so I did a dry run over this before and my buttons didn't work, but now they do.
So are the curly braces required there too?
The curly braces are required, yeah. So even if you have, I think this is good, right? So even if you have a single statement after your condition, you need to put curly braces, which means that if you go back and edit later and add another statement, there's no ambiguity there, right? Multi-value returns, which is something, that when you come from a lot of other languages is kind of a breath of fresh air, right? So here we have, I'll actually go through the whole, so this is a fully complete sort of hello world example here, but I'll go through the full syntax. So before I get to multi-value returns. So the start of every file declares what package it's in, and package main just says this is an executable, right? If you give it an arbitrary name like package foobar, then it's a library. And then you import libraries and your import statements. This is cool, so you can have like a single import line and then just declare stuff on new lines, so you don't have repeated imports or whatever. And then we've got a function here, and the function holes per gopher takes in gophers and holes, both of which are an int. So if you have repeated arguments of the same type, you can put it at the end. You can put it after each one if you want to. And then we have the return types, so float32 and error. Error is a standard type, which is, I think I go into it a little more later, I hope I do, but it's basically, you could associate it with exceptions, right? But anyways, we go and check it out, and if we have the bad number of gophers, we can actually return 0 and then make a new error and return that. Otherwise, we can calculate it and return nil. So the caller here can got it right. Ooh, no. The caller here can assign, holes per gopher and then another variable from the return value. So underscore is super useful. It's a default variable in the language that is just sort of like a garbage bin. So anything you assign to it gets tossed away. You can redeclare it every time. So like right here, it doesn't matter that I've used the colon equals. It's fine. I could call it again and underscore. I could have like underscore, comma, underscore, and that would be okay. It wouldn't care. So you can just sort of use it if you don't care about another argument, another return value. You can just toss it away. So loops. In Go, there is only the for loop. Which, makes for loops look kind of weird, but also it's okay because you can think of, like if you want to loop forever, why bother with while true? Why bother with for colon, right? So there's sort of the three forms here: infinite looping, checking a condition like a while loop, and then doing a traditional for here. Range. Another thing you can do with with for, is with the range keyword, you can iterate over both slices which are kind of like arrays, but you can slice out a slice to get a subsection of it. Slices can grow, so they're more like a list or something from a higher level language. So that's cool. And then I think a lot of things are cool. And then maps, right? So maps are built into Go, and you declare them basically map, angle bracket, the key type, and then the value type. You're limited to what you can use for the key. So it's basically like basic types like string or ints or floats or bools,
It's just a hash.
Pardon me?
It's just a hash.
Yeah, it is a hash, yeah.
Like a Perl map.
Yeah. Yep. Right. So, and what you can do, the range keyword, when you iterate over a slice, the first value will be the index into the slice, starting from 0, then the value. When you iterate over a map, you get the name and the value, right? Or sorry, the key and the value. So we can run it and see your junk here. And what's very nice about this is that this is a language that compiles down to machine code, right? Has static typing, has checking from the compiler, but it has a lot of features that are starting to get quite high level that you typically see in interpreted languages, like built-in maps and built-in iteration stuff. So another very cool thing, one of my favorites is defer. Just a typical open a file, check if something's wrong, and then do stuff with it later. But what you can say is defer and then some statement, and that statement won't run until at the very end of this function, so right when it's exiting. So if we have a complicated logic belowhand with a lot of actual exits out of this function, no matter where we leave, this will still execute. So we can guarantee that the file will be closed when we leave the function. You can accomplish things like this with something like, go to in a label, right? Which you might see in something like C, but then you end up, say what you want about go-tos, but the nice thing that I found about defer is that it keeps your cleanup logic with your declaration logic, right? So we say, open this file, and then once you're done with it, close it. And no matter what we have down below it, no matter what logic we add later, it's always going to get cleaned up.
Does that only work for functions or any block, like an if statement or for loop?
I believe it's any statement.
So it's local scope, then, I guess.
Yeah.
Yeah.
What about when errors occur?
So I don't have a slide about the different types of errors, but typical errors like the error that I did earlier, where you just return, you instantiate it and then you return it, right? There's no throwing where it just sort of bubbles up through the stack. right? You have to explicitly return it. Someone has to explicitly handle it. If you ignore it, then nothing happens. So that's taken care of by this, because if you return an error, it's just like a regular happy path return, right? It'll get cleaned up. In the case of a panic, which is like, we have totally screwed up, we're going to explode, defers will still be executed. So pretty cool. So you can ensure that stuff will get cleaned up that needs to be cleaned up. And the last cool thing I have here is style. From the beginning, Go has had like a default one true formatting style. Love it or hate it, it doesn't matter. That's what you have to use. So you can just get over your syntax arguments and just go forward and write cool code. The other thing related to this is that a lot of stuff that would be warnings from like a linter or whatever are compiler errors in Go. So unused imports, unused variables, your code just will not compile. So Go is designed as a systems programming language, and it was also designed to be highly concurrent. And I want to talk a bit about concurrency, because concurrency is very important for anything you do on the web, right? You talk about like the 10K problem, where you want to handle 10,000 concurrent connections at once, right? At some point, forking a process for each connection or even a thread for each connection just isn't going to work. So yeah, just a nice definition I found of concurrency on Stack Overflow. You can read it and enjoy it. And then let's move on. The important thing to note here, at least for me, is that concurrency is not parallelism, right? Concurrency, you can have a concurrent program with only a single thread. You can use event-based programming like in JavaScript, or event-based programming like with a lot of frameworks you'll have, like Twisted in Python, for example. But parallelism gives you, sort of implicit concurrency, right? If you have multiple threads running, you are concurrent. So Go provides an abstraction that presents you with concurrency, right? You can execute multiple things at once. But in the background, if you have multiple processors available or multiple cores, it will use them. So this is where I get back to the runtime idea. Go has a scheduler built in that'll take care of knowing what cores you have available and which ones of these lightweight threads are actually blocking, waiting for I/O or something else, and will schedule which thread should run at the time on which given core. So it's really nice because you don't have to necessarily think about it, but it still is very good about scheduling things. And the other important part is that it does have this sort of hidden async I/O model. So if you think of something like Node.js, where you do like an open file and then you provide a callback. So once the open has completed, your callback function gets called. Excuse me. In Go, you just os.openFile and wait for the result from it. If if there's another one of these lightweight threads, which I'm hiding the name of for now, it'll execute while the other thing is actually blocking, right? And it'll do that either on a different thread or on the same thread if you only have one thread running. So the lightweight guy is, these are Go routines. And if you know anything about sort of how Linux handles POSIX threads, it was basically like at some point there was, forking, right, and creating a new process. And when it came time to implement threads, it was like, okay, let's take this model of making a new process that has its own memory location, all its own file handlers, and we'll abstract it a bit so that we can sort of use the same kind of model, but we'll just grant it fewer resources, so it shares some with the sort of the forker. So the idea with Go routines is that the same kind of thing where you've taken processes and scaled it back to threads, and now you've scaled it back to Go routines. So they share a lot of resources, like if they're running on the same thread as the forker. But if they need to run on another core and like in another thread, then that's fine. You know, you grant sort of this full all the resources you need for it and run them on the other processor. Not only are they lightweight in resources used, but the syntax is super nice too, right? So the important line here is actually go. And that's all you need to do to launch another async process is just say go function name, and it goes. Right, so that launches off this new go routine and it does what it has to do. Either it returns right away or it loops forever, which I don't have here. But if we run it, you know, you can sort of see like I've got the go routines numbered and then all this junk. So they didn't interleave because it's only running on a single thread, but you know, stuff sort of executes out of order. Another cool thing that I've hidden on this slide is that Go has first-class functions. So what this means is that you can declare kind of anonymous functions inside the body of another function. They will close over the scope of the calling of the function where they're declared, so you can access variables from the outside. And you can pass functions around inside. You can pass functions as arguments to other functions. You can get functions returned, you know, et cetera, et cetera. You know, in practice, it's very nice for doing something like this. Like if you've got a main function and you want to sort of start off a main loop, you can just do it in an anonymous function and say go. So this is kind of strange from like what you might think of in Java when you're executing threads, and you kind of, you know, I could be wrong actually. It's been a while since I wrote Java. I won't even say that. But you don't have access to Go routines. Like you are not the owner of a Go routine when you create one. It belongs to the system after that point. So it's like, okay, I've made this Go routine, and how do I stop it? Well, you don't. The Go routine has to stop itself. And you may want to, like, let's say you're doing a shutdown of a program, you may want to be able to kill your Go routines. It's like, you know, you can't implicitly say, like, kill this Go routine. And this was strange for me at first, and I know it's come up in sort of some other talks as well. But the reasoning behind this, sort of at a low level, is that if you expose a way to control other Go routines, then you need to expose the thread locality of the Go routine. So it starts to limit how easy it is to move Go routines between threads and how you're able to call between them. You know, if I have two Go routines running on the same thread, like in the same processor, and I want one to kill the other, I know when I call it that I can just sort of kill it because it's not executing at that time, right? I have control of the thread. But once it's on another processor, it could just be running along, and I could really screw things up. We'll get back to that maybe very soon. So the point about this is a sort of a philosophy from Go, is that don't communicate by sharing memory, share memory by communicating. So reduce the number of places where you have shared memory that you're, you know, either you're just reading from willy-nilly, or you've got mutexes in place to have people make sure that they, you know, write to it while no one else is. And if you just communicate, you say, hey, here's this thing, you know, then you don't have to worry about actually getting a lock on the resource because you've given the resource to someone else, or you've given them their own copy of it. And how do we do this in Go? We use channels. So channels are very similar to Unix pipes. You basically just open up a communication path between two Go routines, or possibly the same Go routine. And then you just send arbitrary data down through it. So some of the things you can do with it is you can signal completion to other Go routines, you can give work to other Go routines, or you can shut down other Go routines. So, signal completion. This is how we build a channel. Make is kind of like alloc in C, right? So this is actually building a new sort of reference to something, and I'm saying a channel that takes type int. So channels are strongly typed. you declare a channel and give it a type, and that's the only type that you can send and receive from that channel. And then we just, run this Go routine, and it does something that might be resource intensive, and then when it's finished, it just sends this value 1 over the channel. Meanwhile, this guy does his own thing, and then so we have a value that's pushed into the channel, and then otherwise the other syntax here is that we have our channel and we can read something out of it. So writing to and reading from channels by default is a blocking operation. You can actually, if we had come up here, hopefully this is editable, it's not. If you had done make chan int comma 10, then you would actually have a buffered channel, and it would be able to hold 10 values at once. So you'd be able to write 10 things in before it started blocking. So if this guy will actually block until someone reads the 1 off this channel. Likewise, this guy will block waiting for a 1 to be written into it. So it's a nice way that you can have a synchronization point, right? You can simply have this calling guy just wait for someone to write to it, and you don't have to explicitly wait on something. You can just sort of read from this, and when there's something to be read, it'll wait until there is, and then it'll continue on. Another thing we can do, workers. So in my main function, I build another channel of integers, and then I iterate 3 times and just launch this worker function 3 times, giving it the channel and I, and then 10 times. Sorry for my contrived integer examples here, but so we just iterate 10 times and send the value into the channel, and then the workers. I'm using the underscore here again. I could just throw away what I've actually gotten. But the range keyword can be used to read values from channels as well. So it's nice in that way. You just iterate over everything that you can get out of the channel. So my previous concurrency example was pretty lame because they all kind of ran at once, but this one should work out much better. Right, so what we can see here is that the workers will eagerly consume from the channel. So anyone who is, so this guy will push a value on, and then any of these workers who's actually ready for it, the first one will win and read the value off the channel. So a value can only be read once off a channel. You can't use it for like a multicast kind of thing. But it is a good sort of way to do this kind of pattern where you have work you want to give out, and anyone who's free can take it. It doesn't matter if it's the first guy or not that takes it all the time, because whatever, right? If he's busy doing it, the next guy will. So we can see 1 and 2 eventually get in there, then 0 finish up and get some more. And the last thing, this is like one of my favorite ways to use it. It's a very good pattern for when you have sub-Go routines that are doing work and you want to have them cleanly shut down. So we have a for loop that loops forever, and then a select statement. And the select actually selects on 2 different channels with 2 different syntaxes here. So for the actual working guy, we'd say wait until you can read something off the channel, assign it to the work value or the work variable, and then you can operate on it. But as soon as a shutdown channel has any kind of value on it, then just exit, right? We know that if we've read from the shutdown channel, since this is just a single sort of thread of execution, that we're not partway through any of this work. So we've finished up doing a job on that channel. We can just shut down, exit from this worker, and we haven't left anything in a half-finished state. So what I've written here is closed. Let's see if I made this guy editable. Yeah, so if you did something like close, like from the caller, if we did close, shut down, this will close a Go routine, or a channel. And what happens is it actually sends a value onto the channel. But the value is, So what we'd have for these guys is like, so channels always send two values that you can read. There's the actual value, and then there's a state of the channel, opened or closed, like Boolean value. So in the case of shutdown, the Boolean value OK would be false. And everybody who's listening on that channel can see that it was actually shut down. So they'd have like a sort of a default, like nil value for work. Of course, we're talking about shutdown, but they'd have a nil value for there, but then they'd see OK was false. So you can hand out the shutdown channel to all of your child Go routines, and they'll all read the close off it, and they can all shut down cleanly. All right, so now that we're out of concurrency, I'll talk about some of the other kind of things that you might expect from a language. I've been talking about like functions exclusively, right? I haven't mentioned methods. I haven't mentioned classes. There are methods. There aren't classes. What you have is structs, is the closest analogy you have to classes in GoLang. And a struct is like a C struct, right? It's just a composite value. So, the two interesting things on this slide is you do have references and values in GoLang. You can pass everything by value. So if you want to pass a struct to someone and give a copy of it, it will make a full copy. And then they can manipulate the fields on that struct and whatever they want, and you won't see it in the caller. But you can also pass by reference, or have a reference as a struct member. And then you can also embed structs. So this is how you get inheritance, right? If you just say like shutdown is another struct type, if you just declare it at the start, then all of the fields from this type are included in the timer struct, and you can call the shutdown methods on the timer struct. So methods, you can attach methods basically to any type. Typically you'd attach them to structs. So stop is attached to a reference to a timer, and then we can just call. We can close the shutdown channel on the timer. We can call other methods on the timer. But kind of the weird thing is that you can put them on any other type. So if I did, let's see if I can type it. Nope. If you did like type def foobar int, you could make your own kind of int type that was foobar, and then you could put your own methods on the foobar type. Coming down to the end here, so interfaces. This is a thing that kind of caught me up first with Go, but I've come to really appreciate it, is that you declare interfaces and they just sort of attach to any type that implements the interface. You don't need to say that the type actually implements the interface. So I have this sender interface, and it's just one method, and it says send, that takes in an entry and can return an error. So here's an implementer. I've got my AMQP sender here, and the send method, and it's just the same signature, but implicitly this guy implements the sender interface. So any functions or methods or any variables that take a sender type, you can assign an AMQP sender to them, right? What's nice particularly about that, just compared to regular interfaces, which are great, is that if you have a library that you depend on, and it has a type in there that has some method signatures on it, but it's a concrete type, and it's, let's say, final or something, it's very hard to test that, right? You can't subclass it. You can't really easily put some other mock in place for it, because they basically sealed it off from you. But with Go, if you see, okay, well, the code that I'm using implements these three functions, I can, in my own code, define the interface that I use from that type. And then I can call those, and then it's very easy for me to replace that with something else. So you get sort of the niceness of interfaces, but the other classes don't have to play along with it. And that's all. Thank you very much. Any questions? Yeah.
What's the package and module ecosystem model for Go?
So 2 points about that. And the first one is it's excellent. Everything that's available is very mature. Like you'll find a lot of things in all languages, right, that are sort of half-baked, and we haven't used this in production or whatever. In Go, I find that to be less of the case. It seems like people who author modules maybe author one module or two modules, and they take care of what they've written. The flip side of that is that everything that you import comes from like GitHub, or it comes from Google Code or Bitbucket, right? So those are part of the import string. So you'd say import github.com/jbos/foobar, right? And you get the foobar package. But it's unversioned, right? So you can't pin at a specific API version. You are sort of at the whim of if I change it and break the API, or if GitHub is hacked and the code actually changes, you don't really know that, right? There's no integrity there. That is changing. They're adding like support for sort of pointing to branches. So the idea is someone could say have a /foobar, hashtag 1.0 kind of thing, and then you could just follow the 1.0 branch. Yeah.
Is that targeted for the language itself, or is it more like an add-on?
Yeah, that's part of the language itself. As far as add-ons go, there are a number of sort of add-ons that you can get. One is called GoDep, and it's similar to Ruby's bundler or NPM shrink wrap, where you pin down the specific hashes of what you depend on, so the specific like SHA-1 checksums. And then you, instead of doing go-get to pull down your dependencies, you'd run GoDep, and it would read this JSON file and pull down all your dependencies for you. Yeah.
Does it support local copies of modules?
How do you mean?
So instead of actually having it fetch, do a git pull or an SVN CO of something off of an online repository, can I manually have a collection of?
Yes.
Okay, so.
Absolutely. So actually almost to a fault that I don't like. You have Go is very particular about the layout of your project structure. So there's like a sort of a Go path, and then under that you'd have like github.com and then all the different directories. So as long as you just put your junk there, then when you run go get, it's not going to even go to Git. It's just going to like pull it right from there. Yeah. So it's kind of nice because then, it's very easy to, well, it's ups and downs. It's very easy to share among different projects you're working on. Right? Yeah. Two in the back. Yes.
I was wondering what sort of a follow-on to that with the rest of the toolings, like the language, like things like debugging, profile,
yeah.
stuff like that.
So debugging, not so great. You're using GDB. But you'll get all your symbols out properly, right? And GDB is okay, but it can somewhat go across different threads and things, so it's okay. When you get like an actual panic that crashes the program, you'll get stack traces from every single Go routine running. So it's nice to see, and that's the first one will be the one that actually panicked, right? And then you can see where everything else is. So usually the first one is where the problem was, but in case there's other context there, you have that as well. There's profiling tools built in for both memory and CPU profiling. There's built-in unit testing. There's built-in benchmarking. They're both very bare bones, but they work. The absolute best thing that it has is you can compile your binaries with, you can do like go build -race, and it builds in race detection to the runtime. So if you have two Go routines running and one of them reads from a value and the other one writes to a value, it's going to see that has happened, and it's going to actually have the context to know if you've either gotten a mutex for that or if you've had some other kind of signaling in place to make sure that they won't overlap. And it does know. So, if you are just sort of reading and writing from this shared memory location, it will tell you. It doesn't do it statically, so you do have to actually run it, and you have to encounter that case. But it doesn't have to cause a bug before it knows. And so when you run your program with that, it'll just spew it out to standard out, and then just slap a mutex on it, and you're good to go, or replace it with channels. Yeah. The other thing that's really nice is, of course, Go format to format your code. There's Go vet, which will take anything that you're using from the previous version of Go and replace it with the, rewrite your source code and replace it with the preferred new syntax for it. So lots of static analysis as well as runtime analysis. Yes?
Do you split Go routines between machines, or do they all have to be on one machine?
Go routines are on one machine, yeah. So it's all in one process. You may get multiple threads, but you're not getting sub-processes, and it's not cross-machine. So that said, there is a package in the standard library for a binary wire and serialization protocol, and also a binary RPC protocol. So it's very trivial to do multi-machine setups if you want, and you're not concerned about cross API compatibility or cross language compatibility. Yeah. Anything else?
How long did it take you to learn?
How long did it take me to learn? I don't know. I mean, it's pretty easy, right? The syntax is, I find it very C-like and also very Python-like. You don't have to wrap your mind around too many different paradigms. It's just you just launch this other guy, this worker guy, and you throw some stuff in a channel for him to work on, and you're all set. The nicest thing about it, I think, for learning is that where the compiler is so strict, you catch a lot of things up front, right? So, yeah.
Going back to the debugging question, though, isn't I'm going to make my suggestion, and you correct me or the way, because I don't know how to put the question the right way. Is that I'm guessing this would be kind of hard to do some low-level type of debugging where, I worked on projects where, I spend a day trying to figure out the bug, and I finally think, I don't think there's anything wrong with my code. I think it's wrong with the compiler.
Yeah.
And so, I get out objdump -d and start going through the assembly, and when it's C or C++, at least for me anyways, knowing a bit of assembly, I can follow it through and see, maybe, okay, it's done something weird with a virtual function pointer or that kind of thing. I'm wondering though, with Go with this runtime system in the back, I'm guessing that might make it a lot harder to figure out where your code is that it's actually executing in one of these, or does it, or is there
Yeah, so I would say that if you had anything written in C or C++, it was using threads or was doing async programming, it would be as difficult as that. The actual machine code that's generated is, it's just regular old routines, right? So
what I'm getting at, is it easy to find your code? You said there's this runtime part of it, right?
Yeah.
So I'm guessing if it's linked in with 4 megs, it's again, if I've let's say I know where my code is crashing.
Yeah.
So basically, I do an objdump of that particular .o or whatever, right? And the methods on that class, and so it makes it easy. In C and C++, it's easy to do that. Whereas that's what I'm thinking.
Okay, so
if you've got this big binary blob, then how do I find out where in that big binary blob,
and how much of a shell game is going on with this scheduling too?
Yeah. So a few points about that. If you're using GDB to do your debugging, you're going to end up in your code, right?
Yeah.
And you can go down further into your calls or not. Whatever. As far as dumping object files, well, I mentioned that Go is statically linked by default. You can use a version of GCC, which is used sometimes under the hood. And you can actually dynamically link it. So you can just have your object files if you want.
Okay.
If you were building a package that you wanted to have in a Linux distribution where you wanted it to use the system libraries, you would use GCC to compile it and link against all the shared system libraries. And then you would have a 2K file or whatever, right? Very small. And that would probably help to find your problem. And the last thing, I forget what I was going to say. Anything else?
Awesome.
Cool. Thanks everybody.